So quick intro about myself. As Manish said, I started my career as a analog designer. Did various kind of analog designs over 22 years, and then apart from analog design, I did architecture. I did IP lead, chip lead, all these roles, and currently I'm R&D manager for RF processing team in Bangalore, which takes care of analog and RF design. Uh, my journey in NXP started 2 years back, but my journey in radar domain started some 6 years back. And when I started radar, I was actually, I can say I was almost made of questions. Too many questions. The 77 gigahertz radar. What is 77 gigahertz, especially? What is means? I studied radar in our college, undergrad courses, and from there I knew radar. But then what is use of the radar in automotive? Why 77 gigahertz matter? Means how they really in current technologies, means what are the challenges in creating an IP around 77 gigahertz, and there also the things are really a CMOS kind of thing. So very say means a lot of basic questions which I had in mind. And today's presentation is basically I'm trying to cover that. I am not going to go very deep into the design, but I'll try to answer some of the basic questions. This presentation will be for, let's say, 1 hour plus, and you will have your questions. Means there'll be a Q&A session after that. So means hold your questions, uh, and I'll definitely answer those. Okay, thank you. Okay, so first thing, let's start with the name 77 gigahertz automotive radar. And in this, you know, first thing comes is in automotive vehicles, what kind of use a radar has. So radar has started being put into the cars starting almost like in late 60s itself. Okay, and they wanted to radar, you can say radar is basically something, a sensor which can detect the distance of the object, the speed at which it is approaching, and if you do it right, or you let's say if you have right features, then angle of arrival from where the object is approaching towards the sensor. So just think about it. In cars, it makes a lot of sense, uh, especially when we are talking about a new generation of cars where there is a lot of ADAS feature. ADAS features means advanced driving assist features. You can say a step towards autonomous driving. But as I said, radars were used in since 1970, and in starting it was all about, hey, if there is something outside, then alert the driver. Then it started with, that in a lot of cars there are cruise control kind of things which were there, and these things are there since 1995. Means a lot of cars had cruise control since then. So, and there also they try to see what kind of traffic scenario is there and maintain a speed and apply a brake whenever needed. So basic form of radar was there since a long time. Just a minute. I am having so many pings. Sorry about that. Okay, sorry. Okay, yeah. So, but today and going into future, we clearly envision that cars will drive itself, and in that pursuit, what we have already identified is almost like 5 levels of autonomous driving. We call it L1, L2, L3, all the way to L5. So you can imagine the most state of art car today which can drive itself in certain scenarios is still L3. And at one point of time we imagine that, you know, uh, there will not be any driver in the car might not even have a steering wheel uh, going forward. These autonomous taxis, all these kind of things will have almost no driver working with it. Okay, either into the car or remotely. Car just drives itself. And with this kind of scenario, we need a lot of situational awareness. And if you see currently, there are three main technologies which are really enabling that, that situation. One is related to imaging, means cars these days are coming up with so many cameras. Okay, they're like easily, few tens of cameras are there in the car which are there. But the problem, okay, so I'll come to the problem. Then second technology which is decently popular is LiDAR. Okay, it's a laser based radar. And then third technology which is I think very popular is a radar technology. In the radar also, depending upon where the location of the radar, we call it short range radar, long range radar, a medium range radar. But and then ultrasonic also, ultrasonic is there, but yeah, let's say. So current cars are almost deciding driving on their own, these autonomous cars, based upon the combination of all these three type of sensor, and then multiple in numbers. Means a car might have more than 20 sensors. Okay, like these, some imaging, some radar, some lidar. So these are the solutions which are there, and we say that L3 and beyond, all these need to be there combined with a fusion processor at the center, and then car will decide at what speed we have to go, when to apply brake, where to take turn. All these things are going to be, they are already possible and going to be possible. So basically radar is one of the enablers of safety and autonomous driving. Okay, let's see. So means as we say that no, radar, vision, lidar, they all are there to assist a car to be aware of the surroundings. And more or less, they all can do similar kind of things. Okay, they all can detect the object, the range of the object, uh, at what speed they are moving towards you, and at what angle of arrival they come. But each sensor has its own pros and cons. Okay, and for example, let's say with a vision, one problem we can just immediately see is in the dark you might miss a lot of things, including a wall. So a camera cannot really see very well or do very well in the dark. Uh, then some of the other things like very foggy situation, heavy rain. Yeah,
ये chocolate है.
pardon. Okay. Uh, so
Friends,
so
can you mute everyone?
Yes, all are muted.
mm, okay, thanks. So the camera. So these are the limitations. Same way uh, with let's say lidar. Lidar is kind of a very good solution in that term, but it's no, it is, let's say, less susceptible to weather conditions, uh, less susceptible than a camera. But definitely radar is even better. So when it comes to weather condition, for radar it doesn't matter, night or day, rainy or no rain, means foggy or no fog. Okay, all these situations radar really works okay. So weather-wise, it's very robust solution. But then if you see, then there are some issues also because of the resolution. Okay, radars are means not as good in resolving the separation between two objects like LiDAR. Uh, but given the cost, radar, LiDAR, and cameras, you know, uh, LiDAR is a very expensive solution. Means it's almost like you can say 10x or 20x or maybe more. Means that kind of expensive as compared to radars or cameras. So with all the practicalities, given there are so many sensors, okay, two technologies which are very much more widely adopted are cameras and and radars. Ultrasonic is a technology which is always there. It's for very close proximity detection. Sometimes reverse parking, beep beep boop boop kind of things which you hear in your car. Those things have some ultrasonic things, but it has some limited use. In autonomous driving. Okay, so I said that it's radar has certain advantages. It's more robust. It is unaffected by light, weather, and it's very good in terms of when it comes to cost. Some issues in terms of resolution means if there are two objects which are very close, if there are means two objects which are very wide in angle or means so these kind of things traditionally have been issue, but we are moving towards imaging radar. It means a radar which looks like as good as its sensor portfolio. So sorry, its object detection capability looks as good as images of a camera. So this is recent technologies have made these things as a possibility. Okay, so now question comes, means we talked about radar and how it is used in cars, but then question comes about 77 gigahertz automotive CMOS radar. Okay, so let's try to put our attention on 77 gigahertz. What's so special about 77 gigahertz? Okay, so this is a plot which shows the attenuation of any electromagnetic wave in air. X-axis is frequency, which gives that at what frequency, and y-axis is kilometers, is dB. So it shows the attenuation. So it's almost like so if you have to radar or any other sensor, a lot of sensors, they work on these electromagnetic waves being transmitted and received, and based upon that receive power, and we do some calculation. We'll see about it, but first thing we need to know is the air in which these waves propagate. They also are not really homogeneously propagate all the frequencies equally. They have certain characteristic to it, that at certain frequencies it absorbs a lot more energy. For example, if we can see some 60, look around the 60 gigahertz, like just a minute, let me have a pointer. Look around this kind of frequency, or these frequencies around, let's say 180 gigahertz or something. So here, almost for a kilometer, there will be 10 dB plus, or almost like 30 to 40 dB kind of loss will happen in uh, any EM wave at these frequencies. Okay, which is not good. You want to transmit something and receive as much as possible. So this is where you see some interesting frequencies. Something like you see frequencies around, let's say we are talking about 77, so something here you see, this is almost like minima of absorption. Not much absorption of the wave or EM wave, EM energy happens at the frequency. So this is first clue of means a choice of frequency. You cannot just choose any frequency. Okay, to do your transmission, communication, etc. So in fact, you will see that even currently the Wi-Fi, the especially mobile network, they also choose their frequencies in a way that you can really propagate the signals far. Okay, good. Next is about, so we talked about this air itself is very sensitive to certain frequencies. It absorbs certain, but it let go others. Okay, next thing is about understanding the general frequency band. Okay, so what we call RF, radio frequencies can be anywhere between few kilohertz, like AM radio, all the way to even terahertz and even higher. Okay, and everything is electromagnetic wave. Okay, the EM wave, which is AM wave, which is actually propagated at few hundred kilohertz, also is a electromagnetic wave. And even our light or X-ray or anything, all these things are actually electromagnetic waves. And this is the spectrum which we use, just to define. Lower side you see the wavelength, and on the higher side you see the frequency. Like this row, it basically talks about frequency, and this row talks about wavelength. We know wavelength and frequency are related for electromagnetic wave. C is equal to F is equal to C lambda or something. So and in these bands there are many subsection of bands which are used for different purpose. Okay, so for example, we know for radio and Wi-Fi communication we use something from 2.4 to 5 gigahertz. Lately with the 5G, there are new bands which have opened. To till now, most of the Wi-Fi Bluetooth communication happened sub 6 gigahertz. With the opening of this whole new 5G thing, there is a new band of 24 to 30 gigahertz also has opened. Uh, so and then the next thing comes is governments own the spectrum. And the way they decide is there are certain spectrums which you have, if you have to operate, you have to pay. Okay, like for example, these 3G, 4G, 5G, all these spectrums are owned by government. Companies pay hefty licensing fee to operate in the area. And then there are certain spectrums which are free. Okay, government says that you can use it. In that also, there are free, but only government or specific services can use, like defense or airport, airport authorities or airlines, all these kind of usage, or medical usage. But then there are certain spectrums which are free, and this is where the 77 this radar thing comes in picture. So earlier, around 24 gigahertz, some 300 megahertz of spectrum was kind of free and allocated to specific use of automotive radar. And all these early radars were made around that 24.3 to 24.6 gigahertz kind of frequency ranges. And lately, there's one more spectrum which is free, which is from 76 to 81 gigahertz. And almost all over the world, governments have arrived on conclusion that we will use that frequency spectrum for automotive usage. Okay, autonomous driving and cars. So when I use term 77 gigahertz, it's just a popular term. There is nothing specific about 77 gigahertz, because the real spectrum for automotive radars is from 76 gigahertz to 81 gigahertz. And you will see an advantage. Why Earlier, like 10 years back, automotive, most of the radars were at 24 gigahertz. Suddenly they moved to 79 gigahertz. There is a very important, advantage it provides. It gives a lot of challenges. Obviously, if you have to design something at 24 gigahertz versus 79 gigahertz, a huge difference in terms of technical challenges, but it really adds and provides a lot of advantage in performance. And I'll talk about that. But one of the another reason is these are the two bands which were made available by government to use free, because every time you drive your car and someone asks you to pay money, that's not going to happen. So if it has to be feasible, it has to free and dedicated to automotive. We cannot be operating a lot of stuff in that same domain like 5G or communication or okay. So I hope that I explained what's so special about 77 gigahertz because it's free. Okay, good. So as as I said that radar is not a new technology in automotive. Many years it has been, but over the years it's really improving significantly. And this is what it shows. Okay, from left to right. Okay, you see that how radars are really evolving. So first in starting when we were working on 24 gigahertz domain, and we had most of the technologies which were used were silicon germanium technologies, which were actually expensive and heavy. And then the radar processing was a lot less. Okay, there are very little radar could do. It has a low resolution, and all it could do is detect a car. Okay, for example, in cruise control kind of applications, that's maybe good enough. Then technology moved to 77 gigahertz. Although it was not much of an adoption from in the CMOS, it was still SiGe and gallium arsenide kind of technologies which were used, and they made a lot better, let's say, processing. So resolution improved. The moment you get into 77 gigahertz, a problem of resolution improved. And when I say resolution, it's basically, in a road scenario, there are like, hundreds of cars, tens of pedestrians, the cows, walls, all these things can be there, and they all are separate entity, and a radar need to know. It cannot see two radars, two cars just standing next to each other very closely as a one car. It need to know that these are the two cars, and this is what is called resolution. I'm using resolution again and again, but this is the real reason why we need to resolve between the two objects. So the moment you go to 77 gigahertz, I'll show in equations that things really improve drastically in terms of resolution. Uh, but when no, then whole technology is now moving towards CMOS. Okay, and when you have a CMOS, now a radar can do a lot more. Means from detecting a car, it moved to seeing a pedestrian and bicycle also. But now when you go into CMOS, you can do a lot more processing inside chip, and that enables a lot of features a radar can do. First of all, it can actually create a full 360-degree view by adding too many sensors, because cost is less, and you'll see the area is also smaller. The moment you go from 24 gigahertz to 77 gigahertz, we know the area of antenna or patches is proportional to 1 by lambda, uh, and sorry, is proportional to lambda, and higher the frequency you have less lambda or wavelength, and that way the sensor area is smaller. Same time, because moving to CMOS, it's cheaper, a lot. It's a low power. Okay, so you need to be aware of uh, So this is another advantage. And then once you move to full CMOS, you can integrate billions and billions of gates into it, do all sort of processing. And I'll show also that what kind of processing can be done within a chip to identify objects more accurately. And in fact, the situation have come that radars are so potent that they can not only detect a pedestrian, a moving pedestrian, all they can also detect a gesture. Means you are on the road and you see someone, a kid standing on the side of the road. So autonomous car need to take a call that this kid will jump on the road, cross the road, or he will stay on the road. And one way to do it is look at their gestures. What is their gesture? Where they are looking? Okay. All these finer details earlier were not possible, but these days with the highly potent radars, even that is possible. What is the intent? And this is where even machine learning, artificial intelligence, all the things are now coming into radar processing just to detect the behavior, what's the intent of the person, etc. Okay. uh, Coming to radar theory. Okay. I till now, if you see, I really talked about what is automotive radar, why it's used, what's so special about 77 gigahertz, and means what kind of path the radar technology is taking from 24 gigahertz to 77 gigahertz band, and then from SIGI kind of technologies to RF CMOS kind of technologies. So from here onwards, I'll be focusing on how radar works and give you a little bit of an idea about what it takes to implement a radar CMOS IC. Okay, not necessarily CMOS, but let's say CMOS is the technology which NXP uses. Okay, NXP has a very strong portfolio of CMOS radars, a long history. Uh, Current NXP is a combination of two different companies, NXP Semiconductor and Freescale. And in fact, they both had their own radar portfolio, and the companies which merged like few years back, then it became even stronger. And and we are one of the market leaders doing 77 gigahertz CMOS radar. Okay, coming to radar theory, uh, radar is acronym of for radio detection and ranging. We all have, I guess, if you have electronics and communication background, at least I had a course about radar. And the way basic radar works is it has a transmitter, it has a receiver. Often they are co-located, means where transmitter is located, same way, same place receiver is also there next to each other. And they are often antennas who transmit electromagnetic wave, and then there is an object, and electromagnetic wave goes and gets reflected from there, and you receive the electromagnetic wave. And you take that information and do something with the information, and that information gives you some details about the distance of the object, the velocity of the object at which it is traveling, and the angle of arrival of the object. As I said, that these are the three main you know reasons why we use radars. Okay. Okay, so what happens here? So if you can see here, this is where you try to transmit something. These are the two, let's say, different cars shown here, and then you receive this on the same thing. You do the data acquisition, you do the processing. Okay, and after the processing, you identify the objects. Like here you can see, let's say, means I'm not going into further detail right now, I'll go, but let's say somehow you did a signal processing, and whenever in electrical domain you do signal processing, it often comes into a signal and noise kind of thing. The signal is a peak and noise is a floor. So you can see here, as shown here, there are two signals somehow, okay, which are coming here in as a peak, and then there is a bunch of noise which is there. Okay, so you want to really detect two signals. You are not much interested in noise. You are interested in the objects. So then you apply a detection algorithms inside chip or outside chip, inside some radar processor, inside fusion processor, wherever, and often means the term called CFAR, okay, CFAR algorithms, and and basically what CFAR does is it creates some sort of localized cutoff, that above that every signal is an object, below that every signal is a noise. Okay, so you can see here, this is what it's shown here, that there is a kind of envelope which is created above, or curtain which is put here, and above that whatever is visible are the two objects, everything else is rejected. Okay, this is very rough high level signal chain, how radar works. Okay, as I said that in every most of the electronics and communication background students have already studied the radar in their courses. Most of the master students with communication or even some VLSI courses also cover radar, but they all, at least what I know, they all talk about you know pulse Doppler radar, not really about FMCW radar. Okay, so FMCW is the its acronym means frequency modulated continuous wave radar, and I'll explain every term, why, what's frequency modulated, what's continuous wave. But you know industry, and at least automotive industry, has moved away from pulse radars, okay, which many of you might have background and be familiar with. Okay, and the reason for that is the way pulse radar works is they are short pulses with a long silence. Okay, which in the end, if you see that overall power received is low, because for very long time you are not receiving any power. So for example, that's the reason why average power is low, and if you have to really you know increase average power, you really you go and transmit very high powered signals, high powered signals. Okay, these high powered electromagnetic signals, you don't want to risk your body or humans to those. There are limitations in terms of how much power you can transmit per hertz or per megahertz, a kind of thing. Regulations around that, there is a good chance that you may actually violate that regulation. And apart from that, it has some other structural problems in terms of blind distancing, in terms of if you have received a pulse radar signal, the bandwidth needed to process the accurate information for the receiver path is also very high, because these are the very short duration pulses. So shorter the duration in time domain, it has bigger frequency content. Okay, the way it works. Okay, so overall, it is still relevant in defense. It might still be relevant in some of the uh, infrastructure related radars, uh, but slowly and steadily, almost everyone is moving towards FMCW and similar kind of algorithms. Sorry, radar structures. Uh, Especially with automotive, it's almost unanimous that almost every supplier, every chip company, every car, they have moved to FMCW radars. Okay, so just before telling about the FMCW radar, let's quickly understand how really these radars actually work. So often a radar chip or radar, let's say system, FMCW system, what they do is they continuously transmit set of frequencies for some time, and then they stop, and then they, yeah, then they take that data and do some processing. Okay, and sorry, and the reason for that is, first of all, it's the amount of data produced. If you continuously do the measurement is way too high, and then it will be very difficult to simultaneously even process that, because processing itself, you'll see, is huge humongous effort. There's a lot of processing which goes on for every radar signal, uh, and plus most of the situations, okay, you do not need more than 25 hertz of update rate. Means if you sample your environment once in 25, at 25 hertz rate, then you are fast enough. Things do not move, a lot, at least in automotive environment, the car and road environment, significantly in 40 milliseconds. Okay, so if you see 25 hertz is basically 40 milliseconds. So every 40 millisecond, you get a whole picture of a road scenario, okay, in which for 20 millisecond you transmit, and for remaining 20 millisecond, you do the processing, and maybe you cool off as well. So that way you save some power. Uh, this is not a standard thing in the sense that everyone does this thing, but this is a typical situation. A lot of situations demand almost 70% or 80% of the time, you could transmit, and a lot of situations you not just need to transmit only for 25% of the time. Okay, but this is a typical, let's say, situation I'm telling about the way FMCW works. Okay, so next is FMCW principle, and this is where I think we need to take a little pause and understand. So so in pulse Doppler radars, we send, a very short time, very high energy pulses. Okay, and you can see then when pulse reflects and comes back, in between there's a time distance. You can measure, you can measure the distance from there, and same way you do further processing in the Doppler dome. For Doppler frequencies, you get, frequency shifts, and that way you can calculate the velocity, etc. In FMCW radar, okay, it works really differently. So as I said, I use term 77 gigahertz radar, but it's not 77 gigahertz. It's not like there is a frequency of 77 gigahertz which is transmitted. FMCW radar means there's always a band of frequency linearly varied like this. Okay, at time t is equal to 0, there is some frequency, and at time t is equal to, let's say, after 10 microsecond or 20 microsecond or 50 microsecond, there's some other frequency. So you transmit a continuously varying frequency starting from FC and going to FC plus B. And often these frequencies range from 76 to 81 gigahertz, okay, which is the band available. You can do that, or you can do just from 76 to 77, or you can do from 77 to 81. depending upon the applications, depending upon the situations, all is possible. So from an automotive radar, there is not one frequency which comes. There is a linearly varying frequency which is being transmitted from, let's imagine 76 to 81 gigahertz. Okay. And then from there you return back again to 76 and then again send another linearly varying frequency. And this thing is called chirp, like bird chirps. So this is what is called chirp in radar lingo. So and then how really it really does the detection. So as shown here, okay. So a basic principle is almost, you can say, yeah, time of flight kind of thing. Okay. So you send, let's say you send one frequency here. Okay. At this time, x-axis is time, y-axis is frequency. You transmitted one frequency here, and you can imagine there is an object, something, a car in front of your car at 100 meters. Now, if you really do some calculations, because what you transmit is electromagnetic wave, all electromagnetic wave travel at the speed of light in air or in vacuum, and because light is also an electromagnetic wave, so they all travel at 3 point something into 10 power 8 meters per second speed. And if you really calculate how much time it will take for an electromagnetic wave or a light wave to reach to a car and from there get reflected and received by your sensor itself, it's a 200 meters of travel which happened. And 200 meter of travel happened in, let's say, if you calculate, it could be something like, let's say, 500 nanosecond or half a microsecond kind of thing. Now, if you see, in half a microsecond, actually the transmitter frequency or the frequency, internal frequency of the radar shifted from here to here. Okay. Now you are receiving, and I give you example. So I'll use a number, and that way it will be easy. Let's say at some point of time you transmitted 78 gigahertz, and after and your input frequency is continuously changing. So after half a microsecond, whatever comes back will still be at 76 gigahertz, sorry, 78 gigahertz, because frequency does not change in air. But your local frequency, which you are transmitting now after half a microsecond, has reached 78 gigahertz plus 20 megahertz because it's continuously changing. So now in your chip, you have two frequencies. One is 78 gigahertz, which you received, and one is 78 gigahertz plus 25 megahertz, which you have locally. What trick you do is you mix those frequency, multiply those frequency. It's almost like sine omega t plus omega 1 t, which is omega plus omega 1, it means 25 megahertz, 78 gigahertz plus 25 megahertz into sine of 78 gigahertz. If you multiply them together, you get a term of sine of some 25 megahertz into pi t or something like that. Means the multiplication of the two frequencies which are 25 megahertz apart will give you a frequency content which is at 25 megahertz. It will give at higher frequency as well, but that's filtered. So this is the principle on which FMCW radar works. And another important point to note is the frequency. The 25 megahertz which I am talking, I call it a baseband frequency. And if you see, it is linearly related to the distance. More distance you have, more frequency difference between the currently transmitted and received signal you have, because there's more time which was spent in between. So like for example, if something is, you transmitted here and something is far away, and when it is received, you have, you already are here. So this delta of the frequency will almost be this much. Okay. It means more farther the object is, higher the baseband frequency you will get. Okay. This itself gives you a very fair idea about what is the distance of an object. I'm just, things go a lot more, let's say, complicated from here, but I'm just trying to put a very simplistic view about how a FMCW radar, measures the distance of an object. Okay, because time taken from a transmitted wave from radar to reflect and come back is proportional to the frequency deviation it sees, during that time, and time taken is proportional to distance. So it's almost like the frequency you receive at the baseband here, okay, is proportional to, distance. And all you have to do is, let's say you are receiving some frequency, it's a time domain frequency, you do not know what is the frequency of, you are receiving some signal and it's a time domain signal, you do not know what is the frequency of that signal. So what you do is you convert it to digital using ADC, okay, analog to digital converter, and then you do FFT. It means there are FFT engines. FFT is conversion of time domain signal into frequency domain. And when you do FFT, the output of FFT really, gives you the frequency. And that frequency at which you see an object or see a lot of strong signal, that kind of indicates the distance between the sensor and the object you're trying to detect. Okay. Now, a lot of detailed information, okay, which is there about when you really implement it practically, then you just do not want to. There are a lot of things which limit. So there is, first thing is how far you can detect. Okay. So nominally the range we in automotive they want to detect is anything, range. I'm talking about the maximum. Uh, we call the small, SRR or small range, short range radar. So short range radars normally aim for 75-meter kind of detection, and long range radars you want to detect almost 300 meters further down the road. So depending upon those applications, uh, you know, um, you modulate your power. So that's called the range. Another thing which limits the range is some internal implementation at what speed, at what bandwidth is the capability of processing for your chip. Uh, I'm not, it will be a little too deep for this session to explain that. But one, you know, thing which we have been chasing for very long is this. This is, I'll say, the key equation which explains overall migration from 24 gigahertz to 77 gigahertz. One of the main reasons why we want to do that. The resolution of the range of radar is a very simple frequency C, which is the speed of light or speed of electromagnetic waves upon 2b. B is amount of chirp you do here. Means if I'm chirping from or varying the frequency of my transmitter from 76 gigahertz to 81 gigahertz, then my B is 5 megahertz, 5 gigahertz. 76 to 81, 5 gigahertz. Think about it. If you have a very high B, then your resolution is very low. For example, for 5 gigahertz, you actually can have a 3 centimeters of resolution on a car, on the road conditions, something as far as 100 meters. Okay. If you use a 24 gigahertz, radar, then the max B allowed there is just 300 megahertz because of the government regulation. This is the band allowed. But when you move to this 77 gigahertz radar, then max B allowed is 76 to 81 gigahertz, which is 5 gigahertz of B or bandwidth. And if you have 5 gigahertz of bandwidth, your resolution is just 3 centimeter. If you have 300 megahertz of bandwidth, your resolution might be just like almost 40 to 50 centimeter. Means there's a huge difference between 50 centimeters and 3 centimeters. You really want this kind of resolution if you are going to operate in driverless situation. Okay? You really want to differentiate between a big, you know, a big truck and a bicycle next to that truck very close. Okay. So this is what I say is the main motivation why industry moved to 77 gigahertz. And it will not stop here, because now we are like, looking for another free range where absorption in the air is less and noise is also less. Okay, and that range exists somewhere between 110, 120 gigahertz and 140 gigahertz. But good part is there, the B or the free band available is just not 5 gigahertz. Industry moved from 300 megahertz to 5 gigahertz, and now they want to move from 5 gigahertz to 12 gigahertz or 10 gigahertz, even more. Okay, so that they can have a better resolution, which will happen in many years to come, not now, but maybe in 8, 10, 20, 8, 10 years to come. But industry might move towards those frequencies. I already see in universities, some of the European and American universities are doing research in that frequency domain. Okay, so as I say, you receive a signal. Okay, you do analog processing, convert it to digital, and then how really, what do you do in digital? So till now, a lot of things we talked about is very much in analog and millimeter wave or RF design domain, but digital signal chain of a radar itself is a something which is state of art, very high frequency, too many things, and so much of possibility. It's biggest thing which really I'll say intrigue me is the possibility it contains, what all you can do in digital to detect an object and name it like that. So for example, first thing you do is you receive the data, you do the range processing, you try to see, there might be, it's not just one car on the road, there might be 30 cars on the road. You create an whole range. So you create a whole list of objects, and you try to identify at what distance each car is. Then you want to really know at what velocity each of these objects are moving, okay, in the road condition. And then you try to do some sort of filtering. You reject some of the things which are not useful, we call it clutter, and then select only those things which you need to focus on. And then you do angle of arrival estimation. Okay? And in doing all these things, all these millimeter wave frequency, 5G, vision, all these processing techniques come, plus radar specific processing techniques also come in picture. And eventually from all this, what comes out is a target list. These are the objects. These objects are moving at this rate. Now someone need to take a decision. Do I go this way, that way, take a turn, slow down, speed up? All these kind of things are the decision to be taken by a central processor. But radar tells the information about, hey, these are the things, these are the situations you are facing in the road condition. Okay, and this basically just explains a little bit about what we call a CFAR, in the sense that the process of selecting the object and rejecting the clutter or the noise. Okay, I'll not go much into it. Okay, so there is one more interesting information. While you transmit and receive, you get the information about object distance, and if you do further processing, you get the information even about velocity it is moving. Okay, but radar somehow is, if a single transmitter and single receiver is there, somehow it's blind to angle of arrival. So imagine an arc where, like, there are 7 different objects exactly at the same distance, in radial distance from from a car, but they all are at different angle. So if you have a single channel processing, you cannot differentiate between the two if they are moving at same speed. But then you create another level of processing, means now the radars need to be having a multiple receiver channels, and through that you create a resolution in angle also. So for example, the general formula given is, let's say if you have like 4 receiver channels, then your resolution is 50 degrees by 4, or something like something like 13 or 14 degrees, 13 degrees kind of resolution for 4 channels of receiver. But then there's an advanced concept comes, which is called virtual receiver, and that's a MIMO kind of concept which is there. I'm not going to cover it here. It really is a bit of a topic of people who are actually working in the radar domain. But thing to remember out of this talk is that more transmitter and more receive channel you have better angular resolution. And in a road situation, you need all. You not only need to know about how far is the object, at what speed it is coming towards you, but you also need to know in what lane it is. Okay, you don't want to just stop, apply brake when some car which is actually coming in very different lane, or which is coming at the turn, looks like it's coming to you but it will turn. Okay, so angle of arrival is a very key, and in fact this is the one of the differentiator going forward. Better angle of arrival resolution you have, your radar will be considered better. Okay, so and this just tells about number of channels versus resolution. Now coming to my last part of the presentation, which is about radar transceivers and SOC. Means when I say radar transceivers, give you some perspective. So in earlier, this is radar transceiver, okay, which is basically it. You see here, okay, this is a radar chip, and then you have, this is a PCB, and these kind of boxes are there, which actually contain these radars, and these kind of boxes are planted on the all side of the car behind the, you do not see them directly, but because they are hidden behind some plastic covering, plastic casing. But this is how a radar looks like. It has bunch of transmitter and bunch of receiver antennas, and these antennas are patch antennas. So those who know about antenna, they know there are multiple type of antennas, but these are, you can say two-dimensional uh, patches of metal, which act as an antenna. Again, a very complex in no and more like a very interesting design antenna field. uh, and this is a typical chip which you place, and this is why I call it transceiver chip. Okay, because it does transmit, okay, and receive both. Same chip is doing both. Earlier, let's say 10, 15, 20 years back, you almost created, you know two different chips used for transmitter and receiver, and you try to do some tricks on the board to synchronize them. But now almost all major suppliers, including NXP, have their transceiver solutions available in market. Uh, and it gives some idea about this thing. It's like a 4 centimeter by 4 centimeter kind of, 4 centimeter by 4 centimeter kind of, sizing. And that was possible only because we moved to 77 gigahertz. You move to 24 gigahertz, this whole size becomes, almost 3 times bigger. Okay, now, okay, what it takes to design an IC which has, you know, a radar, transmitter, and receiver. Okay, so just in order to understand that, first thing you remember, you see is, first thing is you need to have some sort of application, and this application can stay in software domain also, because a lot of time these radars are complex, soft combination of software, digital hardware, analog hardware, and millimeter wave RF circuit. So RF beyond certain frequencies called millimeter wave. RF up to, let's say we call RF up to 10, 12, 20 gigahertz, but beyond that we call millimeter wave. So 77 gigahertz comes well under millimeter wave. So you know you want a lot of flexibility in programming, how you really program your radar, uh, and you do it in a software application domain. Obviously it runs on, it can be part of, your transceiver, or it can be a separate chip. Okay, uh, then comes the waveform generation. Again, it's some sort of clock generation which can actually chirp, means a clock generation, which actually can sweep, a filter which can continuously generate a sweeping frequency, not sorry, a PLL which continuously generate a sweeping frequency, not just a fixed frequency. Okay, then it takes a lot of, amplitude and frequency gain blocks. You remember, we are talking about 77 gigahertz. This is the frequency, ridiculously high, means you try, means those who have some background or have access, try just transmitting a 10 gigahertz clock from for a millimeter, distance within a chip, and you'll see what kind of effects it has. Now we are talking about 76 gigahertz. The technologies which are there, they're FT. Okay, FT is the term, like you use to define the speed of a particular process node, itself is running into, 100, 200, 300 gigahertz. And typical, let's say, rule of thumb is, if FT is, let's say, 100 gigahertz, the max you can go is 10 gigahertz in terms of circuit operation. But here, with same frequencies using various circuit techniques, you try to go to 76, 78, 81 gigahertz. You transmit it, you receive it, the signal at 78 gigahertz, convert into the baseband, some lower frequencies, do data conversion, then do bunch of processing, estimate reduction. So here I'm talking about what it takes to do RF transmitter. And as I said that you need to generate a frequency of 76 to 81 gigahertz. The next thing is you need to generate a series of gains. You need to have some sort of manipulation of phases around 77 gigahertz. You need to have a power amplifier which can actually transmit 77 gigahertz kind of signals, you know, and there also the power amplifier need to have a peak amplitude 3 times more than the power supply itself. A lot of challenging circuit techniques. 3 to 4 such channels are needed. Same way with receiver, means it really need to be a state of art receiver. And then comes the digital, means whatever you can imagine, means everything can be put in the digital. You need a DSP microprocessor, you need FFT engines, you need a multiple FFT engines, you need microcontrollers, you need application processors, you need memory compression, security engine, some really high speed secure serial communication like LVDS, MIPI, Ethernet, SPI, generic high speed, clocking and infrastructure IPs. All these things are needed to do that. And I'm not even talking about software, okay? Because then software comes even added to that. And there also there are enormous possibility. So you take a radar signal, try to create a scenario on the road, and then you need to have, be very, very creative, because it's almost like one of the most challenging problems in artificial intelligence and machine learning also. Okay, so that's why I say that at currently, not only in NXP, but almost everywhere, a radar CMOS IC is one of the most complex microchip you can create now. There are chips who have more flops, there are chips who have more, higher power, etc. But given the variety of technologies come together and the scale at which it all comes together, it's unparalleled. So this is where I stop and open for questions.